We have 2 hours and 2 lectures. It's 10. I think we might not get through everything, but I really have to go through this quickly because one of my lab instructors found this book on a trip up to Canada. It's called Optical Physics for Babies. They also have Newtonian physics for babies, quantum physics for babies, rocket science for babies, and general relativity. I'll leave it out, but I just think it will be really helpful to start our lecture today with, this is a ball. This ball is red. It reflects red light, right? It absorbs blue and green light. And you learned that yesterday. That's why it's red. This is a clear ball. Colors pass through it. All colors combine to make white light. You did that the first day. The white light contains all the colors. Light travels in a straight line until what? Until it hits something. This is our lecture today. And then it can be reflected. It can be refracted. They don't have diffraction, but that's okay. And so the white light's refracted, it separates the colors, and that's called dispersion. If white light hits a raindrop, it becomes a rainbow because of dispersion. On a sunny or rainy day, you might see a rainbow in the sky that looks like this. It always appears in this order. Sometimes it's reflected multiple times, and you get a double rainbow. And it's in the opposite order. See, babies know more than you. So we imagine rainbows look like this, but they don't. They look like this. And that's because they are made of a whole spectrum of colors. What was the difference? Sharp and blurry. So now you know optical physics.
Oh, great.
Okay, so anyway, I want to start with that. Okay, so we are looking at scattering. We're going to do scattering for a little while. So I thought I would just give an introduction to scattering to get some feel for what scattering is going to look like. And then Kurt is going to jump in and model the heck out of everything. So that will be tomorrow, I think. Tomorrow. Yeah. Okay. All right. So remember we had our slab and we had a thickness and we had an incident radiant power and we had the transmitted radiant power, and some part of that may have gotten absorbed and some part may have gotten scattered. We talked about absorption yesterday. So today, sorry, wrong. Today we're just going to talk about the scattering part. So just like absorption, we have something called scatterance, just like we had absorptance. And it's that fraction of scattered power over the incident power. And if there was no absorption, we could say that that's just equal to the difference, right? You remember that? We did the same thing yesterday, except we defined this in terms of absorbance because we ignored scattering. And we can define the scattering coefficient, which is the scatterance per unit distance. Again, just like absorption is the absorptance per unit distance. Luckily, we don't have an instrument that measures scatter pants. Although we should. Okay, and so we can take the limit and we can solve this and find out that the scattering is related to the natural log of the ratio of transmitted to incident power. So how is this measurement different from A? So I just went through all of the same steps. I got the same relationship essentially with coefficient. But what's different about scattering than absorption that we have in this figure?
It's directional.
It's directional, right? And so there's scattering this way, there's also scattering this way, there's also scattering this way. And so thinking about scattering, if you really want to understand it, you have to think about the fact that it is directional. Okay, so let's let light pass through a thin layer. this same thin layer. And when the parallel beams pass through, you can identify this volume that's being illuminated. Okay. And it's infinitesimal, so it's an infinitesimal volume that we will never achieve in measurement, right? And we can think about scattering of that light coming into that, as the light goes into that volume, you think about scattering at some angle. Kurt, are you going to give the lecture on Greek pronunciation?
Sure. Psi.
Yeah, it's psi. It scatters at the angle. Okay. And then there's also an azimuth angle, which is
Phi.
phi.
There's the saying that there's a Norwegian or Scandinavian squiggle thing that's phi, and if that's what's the saying, if phi is phi, then pi is p. So that's actually a phi because that's the Greek one, not the Norwegian,
Right.
which is phi.
Right. Exactly. And I always wanted to add in there, and no one wants to eat p. But they do want to eat I. Okay, so we have psi and phi. And I haven't shown the azimuth angle here because we're in a plane. And so I feel like I need to go into 3 dimensions. Okay, so we have 3-dimensional coordinate system, X, Y, and Z. And we're going to look at a wedge of the sphere. And there's our angle, psi. So here we're just looking at psi from the vertical, and here it's actually coming out of the board towards you. Okay. And if we projected that into the horizontal XY plane, we can get our phi azimuth angle. Yes.
So the azimuth angle is the angle between the X and Y, and the polar angle is the angle between the Z and Y.
Mm-hmm. Or
Z and
the Z and the XY plane.
The Z and the XY plane.
Okay. So we're going to think about this because if we have scattering coming out at this angle, we want to think about it as not just, as a line, but more as a solid cone, because that's how we would be measuring it, and that's how we will be describing it in models. And so we have to think about it in the same way that we would think about a planar angle. We want to think about a 3-dimensional angle, so a solid angle. So we'll start with a circle. Oh, ignore that for now. And it has a radius, and it has this sort of differential polar angle. Where's my thing? Oh, it's not coming through. Hold on. For some reason, the animation didn't work. Okay, so it has a radius r, and it has this differential polar angle, d psi. And so if we look at that arc length that is defined by the radius and that differential angle, the arc length is just given by r d phi, psi, pi, lie. You don't mind. So in the 3-dimension, let me see if I can do it now. Well, you can animate till you're blue in the face and it will still mess up. Let's see if it will do it now. Nope, it's not going to do it now. Okay. So now you can think about our sphere and wanting to take, instead of an arc length, we want to take a little piece of surface area of that sphere, because that's going to be the surface through which our scattering is going to impact or intersect that spherical surface. Sorry, I'm standing right in front of you. So we have this little differential area here through the sphere. And we can think about that as the product of this side and this side, right? And so the product of this side is simply this little arc length here. Right? The little red part is this little red part. So I did color code correctly, although I did not animate correctly. And so the length of that is just r d psi, right? That's the polar arc. The azimuthal arc, because we're not on the horizon, we're not in the xy plane, is somewhat shorter than it would be if we were. And it's shorter because the we don't quite have the radius of r there. And so we have to compute that. And so if you look at the projection here, instead of being the full length of r, it's r times the sine of that polar angle. Because we have an angle, we have a hypotenuse, and we have a right angle. So if you remember your trigonometry, SOHCAHTOA, right? What's SOHCAHTOA? If we want to know what this length is, it's which one? So it's sine opposite over hypotenuse. So the sine of this angle is the opposite over the hypotenuse, and the hypotenuse is r, right? So the length of that is going to be r sine psi multiplied by the differential azimuthal angle, which is d phi. So that azimuthal arc, the blue length there, is r sine psi d phi. Say that really, really fast on the OMI. Next on. So now you have the two sides of this differential area, right? And so you can compute the differential area as r squared sine psi d psi d phi. And that defines that area. Now, of course, if we want the solid angle, we have to divide the area by r squared in the same way that if you wanted the angle here, you would divide the length by r. So we end up with just the sine psi d phi d psi d phi. And we define that as the solid angle, d omega. So the solid angle, you can think of it as a cone. In this way, we're thinking of it as sort of a square. It has units, not of radians, but of steradians, the solid angle unit. And so you can calculate that for any part of the sphere. Okay. All right. So we're going to look at this scattering and an angular dependence, and we define it as something called the volume scattering function, the VSF. I know some of you had it up on the board the first day, some with like a question mark. I think I know what this is. We call it beta, not as in beta as in the correction for path length amplification that we talked about yesterday. It's a new and exciting new beta. It's a function of the polar and azimuth angles. And it's defined as the power per unit solid angle emanating from a volume, I'm giving you the units, illuminated by some irradiance, right? And so the power per solid angle, per unit volume, per irradiance that's incident on this volume. So it looks like this. There's your volume, right? That's the little volume that's part of your layer. You have a radiance incident on that. It's incident on this surface, ds, right? This part of your little cube volume, the light is incident on that, has units of watts per meter squared. The power per area.
S here is units of area.
That ds is surface of the cube. The volume, as in the volume scattering function. It's the volume that's being illuminated, but it's incident on the surface. That volume has some distance, third dimension of dr. So the volume of of where we're looking at scattering emanating from that volume is just ds times dr, and it has units of meter cubed. So if we put this together, we say that we have this differential power per solid angle per unit volume, which we can now say is ds times dr. And per amount of radiance that's incident on that volume, right? The amount of scattering out is going to depend on how much light is illuminating that volume, right? But we've defined the irradiance as the power per unit surface that it's incident upon. So we can cancel a couple things. What can we cancel in this?
Yes.
ds. So it doesn't matter. ds doesn't matter now. The ds goes away, right? And we can start to group things. So we have the power here, the differential power over the power here, that 1 over x dx formulation, which we've seen before. We know how to differentiate that or how to integrate that. So we end up with 1 over the power per unit length of the power over per solid angle. Yes.
Where did you get alpha?
Where did I get alpha? Oh, bad alpha. Psi.
Yes,
No, phi. Yeah. So it depends on which textbook you're using. And I did a global search and thought I replaced them all to what Kurt's latest version is.
Which I don't even remember. I think I used psi.
I
and
checked it
alpha.
last night.
Yeah.
You used to use psi and alpha, hence the reason for this. And then I checked last night just to make sure you hadn't changed it in the new PDF, and you did.
What am I using now?
Psi and phi.
Okay.
So go change all of your overheads before tomorrow,
All right,
because
well, I'll
I
take a look.
Sci-fi.
sci-fi. Oh, and now everything is made so much easier and happier. Thank you. That is awesome. Okay. So we have this representation, or this definition of the volume scattering function, the power per unit steradian emanating from a volume illuminated by a radiance. And we can plot it as a function of angle. And if we assume some azimuthal symmetry, we can just plot it as a function of psi. And we get something that looks like this. This is crazy. So this says, whoa, orders of magnitude. This is a zero angle, which would be forward or backward scattering. Forward, right? Very small angle here. And then this would be backward, right? So immediately when you look at this, is just a generic volume scattering function for the ocean. What does that tell you? And this is the linear part of the first 3 degrees. Yeah. What does that tell you about scattering by material in the ocean? It's mostly forward. Orders of magnitude, mostly forward. Yeah.
In this equation, does it assume that scattering is uniform?
So yes, if there's an azimuthal symmetry. Otherwise, this would just be at one azimuth angle, right? And when you start talking about individual particles and the scattering off of individual particles, you may not have azimuthal symmetry depending upon the particle, right?
But in those waters, or all waters?
Pardon?
But in like most bulk waters, or all bulk waters, you assume?
We're going to wait for that because you're going to model these and you can think about what the assumptions are, right? Everything's fine until things start aligning. Things of like non-spherical shapes start aligning themselves in flow, and then, yeah. Question?
So like 99.9% of the power forward.
In the ocean, yeah. Because the ocean is filled with lots of particles and most of it's in the forward direction. you know, I mean, forward direction as in, you know, 30 degrees, is a lot, yeah. But definitely in the first few degrees. So how many people, did you guys talk about, you're gonna talk about beam C. You're gonna talk about acceptance angle. So I would like you to pay attention to this because the acceptance angle of beam attenuation meters is somewhere in here. And it tells you what they're collecting. And they're collecting forward scattered light, which has been scattered. Okay.
What's the little tail at the end? Like, is it supposed to?
Oh, now I can't remember where I got this from. This is just, are you going to talk about the enhanced backscattering?
I can, you know, you'll see it in the data.
Yeah.
I mean, it's real.
Okay, so Kurt is going to spend a lot of time talking about the shape of these functions. But yes, there's, sometimes we'll think about it. Sometimes there might not be there.
Oh, okay, great.
Okay, so if we were looking at the forward, we're talking about this part. If we're looking at the side, we're somewhere over here in the graph. And if we're talking about the backward, we're somewhere over here in the graph, just so we're all oriented. Okay, excellent. All right. So if we want the scattering coefficient, we have to integrate under the curve. So we're integrating over the whole solid angle. So all the way down, all the way around, in order to get the entire scattering coefficient. What was T omega?
Solid angle.
Solid angle, right? Do you remember what it was?
Sine, psi, d, psi,
Sine psi, d
d, phi.
psi, d phi. There it is. So we'll integrate over the azimuth angle. 0 to 2 pi. And we'll integrate over the polar angle, 0 to pi. So get you the whole sphere, right? It makes that sound too when you do the integration. All right, so there it is again. So if there's azimuthal symmetry, obviously we can't turn that, just integrate, and becomes 2 pi. And most of the representations that you see will look in this 2 dimensions. Okay. So that's the whole scattering coefficient. So if we wanted to do the forward scattering, we would integrate this part, right? Okay, let's do it. So just changing your integration limits. And if we wanted to do the back part, we would do the back part. You'll see something called the phase function, which is the volume scattering function as a function of angle divided by the integral under the curve, divided by the scattering coefficient. Why would we do that? What would that allow us to do if we took the angular dependence of scattering and divided it by the area under the curve?
The ratio forward to back.
Well, you could do forward to back. That would be, you could definitely do this to this. Or you could do the back scattering fraction, right? Back scattering over total. But if you took the shape of this curve and divided it by the entire area, what units would you have? Well, you would take out the per meter, right? Because you're dividing by B. So we just have units of steradian. So what that does is it changes the magnitude. And it makes it so that you can compare the angular dependence without being concerned about how much scattering something has. So if you wanted to compare a really turbid part of the ocean with a really clear part of the ocean, yes, this one's going to have more scattering, but what's the angular distribution by dividing by the coefficient, it allows you to just pay attention to the angular dependence. So you can look at that, and that's called the phase function.
That would help you determine if your sample
Had
had mostly sphericals or mostly.
Which,
star-shaped,
yes,
something like that.
more forward scattering or less scattering, or what the shape of this, because this gets very variable. And there's a ton of information in there because it's things about the particle that change the shape of the volume scattering. Okay. All right. Oh, and these are all spectral, right? And we used to just have, you know, a one wavelength volume scattering meter, and then we had maybe a couple of wavelengths, 9 wavelengths. And so now I think Emmanuel has, he's talking, do you have volume scattering spectral? Or is that Mike?
We don't have an instrument that does the whole.
That do those parts of
We
it
have,
spectrally.
we have a
Yeah.
3 angle in the back direction, and then we have the list that does the forward part.
At 1 or 2 wavelengths.
Yeah.
Yeah. Yeah.
But we don't, what we are getting today, and I'm gonna have to bolt out to set it up for tomorrow, is hyperspectral 1 angle in the back direction. So you're getting in 1 angle there.
A spectrum.
The whole spectrum.
I think Ken Voss's GASM instrument, which stands for General Angle Scattering Meter, I think he now runs through a sequence of wavelengths on that, but I don't remember.
And it's not the full, it's, you know, sort of here to
Yeah,
here,
it's
as
like
I remember. Yeah.
10 to 170,
Yeah.
something like that.
Something like that.
And there's a least VSF. There is now a commercial instruments that we don't have. That's it.
Yeah. So we're getting there. But you can model it.
It's
So
very rare.
yeah. And as long as there's no data to compare your models to, you're so good to go, right? Believe anything. All right, so it turns out that there's a number of things about particles that are going to influence scattering. It's going to be the size, and really it's the size relative to the wavelength that we have to think about. The shape of the particle, the refractive index, which we're going to talk about relative to the medium in which that particle lies or swims or is suspended. And also the absorption of radiation by the particle is going to affect the scattering. So we'll talk a little bit about each one of these. Okay, so when particles are really small, we call them Rayleigh scatters. It's when their diameter is much smaller than the wavelength of light. And so you can remember we talked about electromagnetic waves and setting up a dipole. So if you have a very small particle and it interacts with this electromagnetic wave, this oscillating electric field, it's going to induce this dipole oscillation. And so I got this figure, and it's very blurry, but I got it from Dariusz Stramski because I think it's really effective. It's showing the dipole and it's showing this motion, right? And you start to see the generation of energy emitting from this dipole. And then this is the dipole back, and it's starting to pinch off the energy. And then you can see it's these lobes are happening, and you can imagine this going all the way around. And it just, this continued oscillation just results in these waves emanating out in all directions. And here's an example of it emanating in this direction here, but it's also emanating in these directions and these directions. And so what happened is by setting up this dipole oscillation, energy is being emitted in all directions, right? Scattering in all directions. So you might think of it something like this, where you have incident light and then scattering in all of these directions for these small particles. And you know, it's relatively similar in the forward and backward directions, a little bit smaller in the 90-degree. And so my question to you is, if you're going to draw this volume scattering function, what would it look like? You want to draw it on the board? That looks like the absorption data you presented today.
It's scattering equally the bottom right one.
Yeah.
Scattering
So
equally forward and back.
and backward and a little bit less at 90. So your dip is at 90. There you go. There you go. Excellent. Right? So that was where I was going to have you do that. This is not a whiteboard, Colin. Can't draw on
It
this.
is. You
Yeah,
kind of
it is.
touch the.
I know I can touch it, but I have some weird electric current, and I stand close and it will start drawing even when I'm not touching it.
Yeah.
I know there's markers here, but just me standing here waving my arms around will advance slides. I've tried this many times. I just can't use these boards.
Okay.
Okay. In theory, I could. So it goes almost equally in all directions. It looks exactly like your drawing. And if you look at it spectrally, what you find is that you get more scattering in the blue than in the red, significantly more. So your volume scattering functions will be different for different parts of the spectrum. It will be lower, right? And so if you were going to draw a spectrum of the scattering coefficient, where you're integrating under the curve, bingo.
The reason you have more scattering in blue because the shorter wavelengths have a higher chance to actually hit a particle and bounce back. Whereas the longer wavelengths would possibly miss it easier.
That is not the reason. I think that has to do with they're setting up, they're more energy, they set up a stronger dipole. Is that not right?
Yeah, I think,
Which isn't the case for the larger particles because other things are happening. But when you're at this Rayleigh level, it has to do, it makes a big difference.
Assuming spherical particle, all of that, it's very, very strongly dependent on the ratio of wavelength to particle diameter or radius. And
I don't think it's because you're getting closer to the length of that the particle's getting, the wavelength is getting longer relative to the particle, not when you're in this.
Think about what the best way to say that
Yeah.
is.
Yeah. And it's interesting because we're talking about like small particles and light, but you can do the same thing with any part of the electromagnetic spectrum. You know, you can talk about it in terms of microwaves and baseballs and things like that. But I thought it was because there's more energy to scatter. It sets up a stronger dipole, so it scatters more. Larger particles will actually have the electromagnetic field going through it. This is actually, they're much bigger than this, but it will be setting up dipoles within the particle, which can emanate. But you also get into this other kind of process where they're interacting with it as a shape as opposed to just an individual dipole. And so you get interactions at the surface, you get interactions across the interface, you get interactions within the particle if it's not uniform, and it turns out you get interactions around it. So you will hear people say, oh, it's a me scatterer, or it's me scattering. And I think it's just really important that there's a theory called me, which is spherical particles, homogeneous, randomly, uniform indices of refraction, et cetera. And you can predict scattering off of those individual particles, but it's not a me scatter. It's just a theory that describes scattering. So it's large particle scattering and small particle scattering. There's a model for large particle scattering developed by a German named Me, who isn't me. And scattering at this stage is composed of this refraction within the particle, the reflection in the backward direction off of the interface, and also light that's traveling near the particle but never actually touches it, but gets impacted by it, called diffraction.
Is the ratio between diameter and wavelength for large particles, that would be much greater than 1?
Yes.
And then for small, it would be
Much less than 1. And when you're in between, it's the Rayleigh GANs, and there's other theories that take you in that intermediate zone, which of course, these are these are much more submicron particles are the Rayleigh. Okay. So this is a figure from a very old book by Dira, but I like it because it shows like all of these different things that can happen to light rays as they interact. They can reflect off the back. They can just refract and go forward. They can doubly internally reflect and come out in the backward direction. So this is scattering in the backward direction just off an interface. This is scattering in the backward direction, having gone into the particle and come back out, right? And they'll contain different pieces of information because this process contains information about the inside of the particle and this one doesn't. Okay, so refractive index. So the speed of electromagnetic radiation in a vacuum is like 3 × 10⁸ meters per second. It turns out that as it enters other medium, the light waves slow down. Okay, and we define the index of refraction, and so it's this property of the medium, and it's just the ratio of the speed of light in the vacuum compared to the speed of light in the medium. And if you look at that, in air, it's 1 because it's close, right? For our purposes. And then as you go to water and seawater, you can see that it slows down pretty significantly when light is moving through water. We typically parameterize the refractive index in the ocean, not using this, but using the ratio of the index of refraction of a particle relative to seawater. So our numbers tend to be smaller, say 1.05 or 1.02 or 1.005. So you just have to, when people talk about index of refraction, make sure you know which one they're talking about. The absolute index of refraction is the one relative to the seawater medium. Yeah.
Which typically, and I know this is a broad general question, will we say, do most people compare to
We
the
will all be
ocean?
talking about this one.
Okay.
Yeah.
So most of the time it,
Mhm.
okay.
Yeah. Okay. So unless we're talking about bubbles, it's going to slow down. And when that happens, the wavelength shortens. So I use this figure, and I can't even remember where I first saw it. It was from some textbook, but I did find a clean one online. And it demonstrates this with a marching band. So each dot is a marcher. They have to march in line because that's what marching bands do. And they have to have a separation so that people with the trombones don't hit the people in front of them. And they're marching down the road in this parade. And for some crazy reason in this parade, the pavement ends and now they're walking in sand. So you're marching along, playing your instrument with all of your pals in line, marching along, you hit the sand, and then suddenly it's harder to walk, and so you slow down. Right? So when the first group came off, they slowed down, and the group behind them caught up to them quickly because they were still walking on pavement. So what you notice is that the wavelength, the distance between the crests, the line of people is the crest of the wave, shortens up. They don't hit them, but they shorten up. And that's what's happening to waves as they propagate from one medium to another with a higher index of refraction. They slow down, so the waves will shorten. I usually have my students do this in the classroom, but our classroom's too small. Now, what's even crazier about this parade is what if they were initially not even walking along the road, but sort of across the road? What you see is that the first person in line on the crest that steps off into the sand slows down. The rest of them keep marching fast. The next person steps off and they slow down. And so what you end up with is the direction of propagation changes because the wave slows down and shortens up as you go from one medium to another. And then the most important question to answer is, why are they marching here on this strange road that ends in sand, and where's the audience? But what it shows you is that if you have electromagnetic radiation propagating from seawater to the interface of a particle, and that particle has a different index of refraction, which causes the wave to slow down, the wave will bend, and that is scattering. What would happen if they picked up here with more pavement? This first line of people, the crest, would step onto the pavement, and what would happen? They would speed up. So they would increase the distance between themselves and the crest behind them. And they would end up looking like this on this side. This is a traffic pattern. This is what happens when you're on a highway, you go to town and you go to on the highway again. Yeah.
Does the wave lose energy or is it conserved?
It's conserved.
Because the speed of light also decreases.
Exactly. The marchers may lose energy because they're walking through sand, but that's because they're not light. All right. So the index of refraction impacts how light reflects off of that interface. That's Fresnel reflection. And Kurt's going to talk about this when he talks about interface effects. Just know that it exists, but it determines the amount of transmitted power versus reflected power on incident. So that's how we get to the reflection part of scattering, the refraction part of scattering, and then we have the diffraction part of scattering. So do you guys remember the diffraction in the first lab that you guys did? You had a little diffraction. What was that experiment?
Light going around the circle with angles, right?
It was through a slit.
It was a slit.
It was putting a laser through a certain 500 lines or 1,000 lines, and the dots that come after the passing through, it was depending on which wavelength we were using, the red color or the blue color.
And you would see different dots
Different,
coming
yes.
off of that. Yep. So that was one experiment. There was another one.
Oh, the hair.
Whose hair?
Yes.
I don't remember whose hair.
It was Charlotte's
Charlotte's
hair.
Charlotte's hair.
Charlotte's hair created diffraction
Yes, it created a pattern of diffraction.
of light and dark, right?
Yes.
Because the light wraps around, right? Just like a water wave will wrap around a jetty. Doesn't go through the jetty, right? That would be bad for the jetty designer. Okay, so you get this bending around, and it turns out that diffraction is pretty independent of index of refraction because it doesn't interact with the particle. And if you look at diffraction, that's this part of the volume scattering function, right? It's that real forward part. So this is a very weird angular diagram. Light's coming in, there's the big particle. Most of the scattering's in the forward direction. But this part here, that 10 degrees, is dominated by diffraction and not by near forward angle refraction. And so it's the large particles that have the diffraction. And this is going to be an interesting phenomenon, the fact that it's independent of index of refraction. Because the index of refraction, you can imagine, is determined by different characteristics of the particles, right? Phytoplankton are basically bags of seawater. So they have a very low index of refraction compared to seawater. Mineral particles have a very high index of refraction because they're comprised of rock pieces, right? But what would that mean about their diffraction if they were, say, the same size? Should be the same. The other parts might not be the same. That would be the same.
But you still need a different index of refraction.
Yes.
Like,
Yes. Yes. So the large particle scattering is proportional to the projected cross section of the particle. So if you have a spherical particle, it doesn't matter its orientation relative to, say, the incident light, right? It's going to scatter the same. But what if you have a long, thin particle this way towards the incident light versus this way towards the incident light? It makes a big difference, right? So phytoplankton, their scattering properties for individual cells is very different if they're facing, which part of their cross section is facing the incident light. Okay. The angular dependence is focused primarily in the forward direction because of diffraction for scattering by large particles. And so it looks something like this. So if you look on the board, I sketched very badly, it looks like, just the volume scattering function, right? So it's primarily in the forward direction. That's due to diffraction. There's scattering in the backward direction. Sometimes there's a little minimum around the waist area. And so here's some volume scattering functions. This is from Kirk's book, looking for, so you see different magnitudes of the volume scattering function, integration under the curve, different scattering coefficients, probably because there's just more particles in there, but there's certainly large particles in there because we have this really strong diffraction in the forward direction. Right. Just that. Okay. And it turns out that unlike the very small particles, which have enhanced scattering in the blue compared to the red, the larger the particles, the more it scatters light equally of all wavelengths. Why do you think that might be? You had particles that were very large relative to the wavelength of light, and you sent blue light through and you sent red light through. They respond to the wave similarly. There's so many wavelengths within the particle's diameter that the differences in wavelength between blue and red are very small.
That one slide.
Yes.
Miscolored.
That's just the magnitude of scattering. It's just fewer particles, more particles. It scales with particle concentration. Yeah.
Sorry, could you also explain the lambda to the power of -4?
The approximate power of approximate.
Yeah, that was for small.
For small particles. Because there's more energy, it sets up a stronger dipole. And they are small relative to the wavelength which is going around them. So the differences in energy are very big for those very small particles.
So the scattering scales in that.
So what about particles that absorb? So we have the imaginary index of refraction, which they call n prime, relative to the medium. Ooh, that should be an m. And so you can imagine that we have some of this light penetrating into the particle. And if it penetrates into the particle, what's going to happen to it? It's an absorbing particle. Some of it's going to get absorbed, right? And if it gets absorbed, we're done. There's no opportunity for scattering because it's already absorbed, right? So in the case where you have some absorption, how is it going to impact scattering? Which part of the scattering is it going to impact? Is it going to impact the reflection? No. Is it going to impact the diffraction? No. It's going to impact the refraction part of scattering. So if you have a phytoplankton cell and you send in blue light or you send in green light, of the part of light of the scattering that is refraction, which one is going to be most impacted by absorption?
Blue.
Blue. Why?
Because absorbed.
By
The
chlorophyll.
Yeah.
Right? So the amount of light coming out in the refraction part of scattering will be less in the blue than in the green. So if you were plotting your scattering spectrum, what's it going to look like? Flat, heading to the, so 400, heading to 440, it's going to have a dip. And you're heading to the, in the green, it's pretty high because it's not being absorbed. And then you head to the red and this comes back. So you actually can see the effects of absorption It's not exactly, there's some other processes that go on, anomalous dispersion, so there's some shifting that goes on, but essentially you have less scattering in the spectral bands where you have absorption. So you want to be really careful where you select those bands. And in the extreme, if you had a perfectly absorbing, 100% absorbing particle, you would really only see diffraction and maybe some reflection. So very strongly absorbing particles don't have a lot of refracted particle scattering, and particularly scattering in the backward direction. Phytoplankton are very inefficient at backscattering because light that enters into the phytoplankton gets absorbed. And so in addition to having a low index of refraction, they have a high imaginary index of refraction. Okay. All right. So particle size, particle composition, particle shape, and internal structures are all constituent properties that you need to consider when thinking about scattering. What time is it? 10:40. Okay. I'm going to quit at where are you at? I have some exercises we can do, but we don't have to do them today.
Take chunks out and put them into other lectures too. So
Let's see if there's one more thing I want to do. Let me just check and see what I can do with that. Okay. We can talk about the list. We can talk about who's a scatterer. Okay.
And while Colin's looking at that, we've seen all these things like particle composition and size and shape and whatever that affect scattering. Which of those things would you expect to correlate well with the chlorophyll concentration? You've learned somewhere along the way that absorption of phytoplankton is very strongly correlated with the chlorophyll concentration. But how about scattering? You know, I can have a certain amount of chlorophyll in the water, 1 milligram per cubic meter, but that could be a lot of small particles or a few big ones. And the scattering by the small particles is going to be much different than the scattering by the big ones. Or they could be spheres or they could be long chains and have the same chlorophyll. So scattering does not correlate very well with chlorophyll concentration because of these other effects like size and shape, whereas absorption is very strongly correlated with chlorophyll. So that makes it really hard to come up with a little bio-optical model that says, take the chlorophyll, plug it in, and get back the scattering coefficient. It's just really hard to do. We'll see that tomorrow.
So I was going to have you guys do this as an exercise on the board, but I just want to it kind of gets at size. So we'll be talking about size spectra, and these are just a way to characterize the size spectrum. But think of it in terms of a community that is dominated by small particles, like the nanoplankton, but picoplankton maybe, versus communities that are dominated by microplankton, right? They give rise to different volume scattering functions. And you can see that the big cells tend to have much larger forward scattering because of diffraction. And the small tend to have much higher relative backward scattering because they start to get more into the Rayleigh-ish type of scattering. They're more efficient in the backward compared to the forward direction. And so in thinking about that, imagine you have a community of phytoplankton that are undergoing synchronous division, which means that they grow to a certain size, replicate, and then divide into smaller cells. What would that do to your volume scattering function? Yeah, exactly. So you could actually draw a line on your little graph. If that was the first case scenario, that's the big cells. Now, how would that change? What parts would change if you're now going to small size?
If you are big, it would be odd. If you're big, it would be like this, and if you are small, it would be like this.
Opposite.
Okay.
If you're big, you have more diffraction.
Okay.
So the forward part goes up. And if you're small, you have comparatively more scattering in the backward direction. Okay. That would be a cool thing to test. I've never seen that published. Okay. The last one, if you hold the index of refraction constant, look at what happens to the diffraction. So you're allowing the index of refraction to change. So this is an index of refraction like phytoplankton. Here's an index of refraction like a mineral particle. Actually, it's more like this. But if they're the same size communities of particles, the diffraction doesn't really change. Diffraction is relatively insensitive to the index of refraction. But look at the backward direction. Phytoplankton, very weak backscatterers. Mineral particles, very efficient backscatterers. Same size particles, just different composition. So you're transitioning from an environment from mineralic particles out to phytoplankton as you head out to the ocean. Say in the magic world that they all have the same concentration and size, you would see a very strong change in the volume scattering function. Okay. So what would it look like?
Like that one, miras.
Go ahead and sketch behind you. Right, excellent. Same in the forward direction, very, very enhanced backscattering by the mineralic particles. So the volume scattering function is very variable depending upon particles. But again, if it's variable, it's an opportunity for exploiting that information. Okay, I'm going to quit there. We're going to take a 10-minute break and be right back in there or back in here. Where do you want to be?
Is it here okay?
Do you want the whiteboard?
I'm gonna go electronic.
Okay, so you can go anywhere.
I can go anywhere, wherever people are more comfortable. Here, leave our stuff.
Okay, good. So I will say that this example that we just did here with the